Hi, my name is Luis Bowser, and this is my project for CS6795. I built a computational cognitive simulation that asks a simple question. When you take the same information and present it as plain text, as a bullet points, or as a labeled hierarchy, what does each format do to working memory load and recall? This question comes up constantly. AI assistants, documentation sites, and educational tools all present identical content in different structures, and that choice is usually made on style rather than on any understanding of what it costs a reader cognitively. Cognitive load theory tells us that poorly structured material wastes limited processing capacity, and work by Cohen and Miller shows that working memory holds only about four chunks at a time. Chunking is how people stretch that limit by grouping items into larger units. So my research question is, holding the content fixed, how does the number and arrangement of working memory chunks that a format imposes determine cognitive load and recall? And at what point does adding more structure stop helping? I built the model in Python with four components, each grounded in a specific piece of theory. The first is a representation parser. It takes the same content and renders it three ways, then counts how many working memory chunks each format creates. Plain text gets roughly one chunk per item. Bullet, bullets group items into small sets, and the hierarchy uses its category labels as chunks, so its count is just the number of categories. The second component is a cognitive load model. It splits the load into an intrinsic part, which is the content and stays the same across formats, and an extraneous part, which grows with the number of chunks and shrinks with structure. Third is a capacity constrained buffer. The first four chunks encode at full strength. Anything beyond four is weakened geometrically as if it has to push something else out. This is the bottleneck that separates the formats. And fourth is a decay model. Recall fades exponentially over time, and it fades faster with extraneous when extraneous load is higher. What I want to stress is that the ordering of formats is never hard coded. It falls out of how the buffer and the decay rate interact. Looking at the center column, you can see the three representations of the same 12 items. Plain text has 12 chunks, bullets have four, the hierarchy has three. The recall curves show what means over time. Plain text starts lower because it overflows the buffer, and it decays faster because it carries more load. The hierarchy starts at full recall and fades the slowest. Across all four content sizes, from six items to third up to third part, up from six items up to 30, the ordering holds. Hierarchy best, then bullets, then plain text. But two less obvious things came out. First, structure only helps up to capacity. 30 items in five categories, the hierarchy needs five chunks, which is past the four chunk limit, and its initial recall drops to 0.92. So even good organization starts to fail once the groups themselves exceed capacity. Second, the benefit of bullets depends on how item count aligns with chunk size. At 20 items, bullets need seven chunks, which overflows, while a four category hierarchy still fits. I also ran a sensitivity analysis sweeping capacity, the overflow penalty, the decay coupling, and the bullet group size across 432 combinations. The ordering held in every single one. Finally, I added a second experiment to fix a blind spot. The baseline ignores how many items sit inside each category. When I gave it a lopsided hierarchy with 10 items in one category and two in the other, it reported perfect recall, which is clearly wrong. The extension penalizes oversized categories the same way it penalizes too many categories. With that fix, the lopsided hierarchy falls below bullets, meaning a hierarchy with badly chosen groups can actually be worse than a flat list. The unifying idea is simple. Format effects are competition among chunks for fixed capacity. A small, transparent model recovers the predicted ordering as emergent behavior and adds testable predictions about where structure helps and where it fails. The most important next step is fitting the model to human behavioral data and testing the capacity ceiling prediction with a real study. That would move this from a model that is consistent with theory to one that has been checked against behavior. Thank you.